It is critical to design microservices with the ultimate business objective in mind. This may require teams across organizational boundaries to come together and design the microservices jointly to service a common business purpose. We should design for failure. There are several design patterns that address failure and ensure stability. One is the circuit breaker pattern, which is commonly used to ensure that when there is failure, the failed service does not adversely affect the entire system. This would happen if the volume of calls to the failed service was high, and for each call we would have to wait for a timeout to occur before moving on. Making the call to the failed service and waiting would use resources that would eventually render the entire system unstable. The circuit breaker pattern behaves just like a circuit breaker in your home's electrical system. It trips to protect you. Calls to a microservice are wrapped in a circuit breaker object. When a service fails, the circuit breaker object allows subsequent calls to the service until a particular threshold of failed attempts is reached. At that point, the circuit breaker for that service trips, and any further calls will be short-circuited and will not result in calls to the failed service. This saves valuable resources and maintains the overall stability of the system. Another design pattern is bulkheads. Just like a ship's hull is composed of several individual watertight bulkheads, so that if one of the bulkheads gets damaged, that failure is limited to that bulkhead alone, as opposed to taking down the entire ship. Similar partitioning approach can be used in software as well to isolate failure to a small portion of the system. The service boundary, that is the microservice itself, serves as a bulkhead to isolate any failures. Breaking out functionality into separate microservices serves to isolate the effect of failure in one microservice. The bulkhead pattern can also be applied within microservices themselves. For example, consider a thread pool being used to reach two existing systems. If one of the existing systems started to experience a slowdown and cause the thread pool to get exhausted, access to the other system would also be affected. Having separate thread pools will ensure that a slowdown in one existing system will exhaust its own thread pool only and not affect access to the other existing system. Now let's move on to decentralized data management. Ideally, you want every microservice to manage its own database. This enables polyglot persistence using different databases and different types of data stores, such as SQL, NoSQL, Graph for the microservices. At the same time, to preserve the ACID nature of a transaction, we may need to have more than one microservice use the same database. So essentially, for practical reasons, to keep the atomicity of a transaction, more than one microservice may end up using the same database. In that case, we need to be careful while sharing a database because the two microservices need to know about each other, and changes in the shared database need to be coordinated between them. In this situation, the two microservices do not have bounded context. In general, the level of sharing between microservices should be limited to make the microservices as loosely coupled as possible. Now let's talk about discoverability. Microservices architecture requires making services reliable and fault-tolerant. This implies we should construct microservices in such a way that as the underlying infrastructure is created and destroyed, the services can be reconfigured dynamically with the location of other services that they need to connect to. When the new service instance is created, the rest of the network should be able to find it and start to communicate with it. Services in Cloud Foundry, the open source PaaS on which Glumix is based, are advertised to the cloud controller to make it aware of the existence of a new service and its availability for provisioning. So this makes discoverability quite easy. Inter-service communication design. When microservices are spread across deployment containers, how do they communicate with each other? They can use synchronous HTTP-based mechanisms such as REST, SOAP, or WebSockets, or they can rely on asynchronous messaging using a message broker. Asynchronous messaging decouples the services from each other, enabling the sending thread to get on with work while the messaging system keeps the messages safe until it can be delivered to the destination. Another advantage of using messaging is that the back-end applications behind the queue can distribute the workload among several clients. Implementing one or more instances of a back-end worker application enables the front-end app to continue its work without the need to wait for the back-end application to complete. Now, how do we deal with complexity? We can do so through testing, monitoring, and DevOps. Testing a complex system requires suites of unit and integration tests and a testing framework that simulates failed or failing components, service degradation, stress testing, and the overall system's behavior over the course of a typical day. In addition to conventional monitoring systems, well-designed services can provide additional health check information using publish, subscribe over a message queue. In this way, information can be collected by the monitoring service, providing rich health and configuration indicators. These indicators can be used to ensure that the service has enough capacity to serve current request volume, and we can compare current performance against expectations. Custom health checks can be registered to gather additional data, and all the information collected can be aggregated and displayed in the monitoring dashboard. Now, going on to DevOps. The operations challenge of keeping microservices up and running means that you really need high-quality DevOps skills embedded within your development team. Let's move on to evolutionary design. Microservices architecture enables such a design approach. The core idea is that you can introduce new features and capabilities in your application by changing a single microservice. You only need to deploy and release the microservices that you have changed. And this change only affects the consumers of that particular microservice. And if the interface has not changed, all consumers will continue to function without any interruption. Because microservices are loosely coupled, they are small and focused and have a bounded context, changes to them can be made rapidly and frequently with minimal risk. The ease of upgradability of a microservice enables evolution.